And so our last section we're going to look at for this week is section 3.5. Again, it'll extend some of the concepts we learned using like synthetic division and rational root theorem with real numbers to imaginary or complex numbers. Okay, we'll also do a quick review of complex numbers. Okay, you've already had this written down. I'm just reminding you again that if something is a root or something is a zero of a function, it means that's the number you plug into the function and get 0, or that number is also an x-intercept. Okay, so just reminding you of something we've said a lot of times. Okay, if a polynomial does not cross the x-axis, then there are no real roots. Okay, let's look at this one. Y equals x squared plus 1. If you were to graph this, it's a parabola shifted up 1 unit. It would look just like this. Is that graph ever going to cross the x-axis? No. So then we know something about the answers we're going to get. So let's try to set this equal to 0 and solve it. And see what happens. So we get 0 equals x squared plus 1. What's the first thing I would do to solve that equation? Subtract 1. And what's the last thing I would do?
Find the square root.
Yeah, find the square root. Square root and square cancel. So I get x equals the positive and the negative square root of negative 1. What's kind of weird about that answer that we haven't done yet? Yep. Yeah, if we're working with real numbers and you try to take the square root of a negative, okay, watch what happens. Square root of negative 1. In fact, it tells me basically what kind of answer it is. It's not real. So it has to be something else. Okay, well that's where imaginary numbers come in. So this is a definition in this red box. Okay? If we want to take the square root of negative 1, we basically have to invent something that's the square root of negative 1, and we call it I. Okay, you can't prove why that's true. It's just that just is. It is what it is there. It's kind of like in geometry. There are certain things you can't prove. Like, you can't prove that parallel lines never cross. That's just the definition of parallel lines. That's the way it is. Parallel lines just, they don't cross. Okay? I equals the square root of negative 1. That's the way it is. So then, if we use that as kind of our foundation, we can figure out other things. All right? So let's see if we can figure out I squared. Okay, so I just said I is the square root of negative 1. So I'm going to plug that in. Yeah. Yeah, it would be negative 1. There's I. Okay, square root of negative 1. I'm going to square it. Well, when you have a square and a square root, those two things do what? They cancel each other out. And all you're left with is whatever was under the root. So I squared is negative 1. Okay, we could figure out I cubed, I to the 4th. There's a nice pattern. But really the one that's going to come up a lot today is I squared. So I squared, if you ever see something like that in a problem, and that's part of your answer, you should never leave I squared in your answer. Always simplify I squared to negative 1. So let's try plugging I into the equation we just had and watch what happens. Plug I in for x. I squared is what number? And what's negative 1 plus 1? So that proves that I is a what of this equation? It's a 0. Yes, if you plug in I, you get 0. I is a root. I is not an x-intercept. Okay, imaginaries, you can't see them. Okay, on the graph. Okay. So any questions on that? Now, I isn't the only root, because I'll tell you something and I'm going to write it later, but imaginary roots always occur in pairs. So if you have one, you have another one. You never have an odd number of imaginary roots. Okay? But once we know one of them, the other one is extremely easy to find. Okay? So we'll talk about that. All right, so we'll do a quick review of complex numbers, and then we'll actually get into the stuff we're going to do today. Okay, so complex numbers are generally written in this form: real part and then imaginary part. So in this problem, A is my real part, B is my imaginary part. Okay, not the I. The I is just there to tell you what's in front of it. That's the imaginary part. Okay, so down below I have all different examples of complex numbers. Okay, let's take a look at 2 plus 3i. Can anybody tell me what the real part is in 2 plus 3i? Yeah. 2. And how about the imaginary? 3. Okay, so the real part is 2, imaginary part's 3. Let's look at 3i. What's the real part of 3i? 0. Think of it as 0 plus 3i. There's no real part. And the imaginary part? 3. How about 4? What's the real part?
It's only 4.
It's 4. And what's the imaginary part? 0. All right, so the first 3 are kind of special cases. The first 2 are what we call pure imaginary numbers. Okay, those are pure imaginary numbers because they have no real part. The third one is what we just call a real number. It has no imaginary part. And the fourth and the fifth one are what we call they're complex numbers. They have both a real and an imaginary part. So if you're trying to kind of visualize, how does everything fit into the number system? Well, the big overall category is complex numbers. And under complex numbers, you have your reals. And then you can break that down. I think we've done this before. You've got your rationals and irrationals. And then within your rationals, you have your integers. And within that, you've got your whole numbers. And then within that, you've got your counting numbers. Okay, so you've got all your number sets under the reals. And then under complex, you also have your imaginaries. So everything is a complex number. Okay, everything. Sometimes the real part is 0. Sometimes the imaginary part is 0. Sometimes both parts are not 0. Okay, but that's where reals and imaginaries fit into the big picture. Okay, they fit under complex numbers. All right, that's not too important. You really don't have to write that down, but it's just saying 2 complex numbers are equal if the real parts match and the imaginary parts match. These are not equal. Part of them is equal. Okay, the real parts match, but in order for 2 complex numbers to be the same, both the real part and the imaginary part has to match. All right, so this is more important. When we're doing arithmetic with complex numbers, you can treat I like a letter, but I want you to remember that I is a number. Okay? Just like this. Yes, that's a letter. It's a Greek letter. It's the Greek letter pi. But in math, it's not used as a letter. It's used as a symbol that represents 3.14. Okay? I is a letter in the English alphabet, but in math, I is used as a symbol that represents the square root of -1. Okay? So keep that in mind. I is really a number. But it kind of helps if you want to think of it as a letter when you combine like terms. So like if I said to you 2x plus 3x, you get 5x. Well, it's the same thing if I said 2i plus 3i. It's 5i. Right? So you can think of it like a letter when you're combining like terms. When you multiply complex numbers, a lot of times I squared comes up because you end up doing the distributive property. You end up multiplying i's together. All right, so anytime you multiply, use your distributive property. Some people call it FOIL. Okay, and when we get to a division problem, Okay, the big thing with division complex numbers is you never want to leave an imaginary number in the bottom. You're not allowed to leave I in the denominator. So we need a way to solve that, and that's what a conjugate will do for us. It'll clean up the denominator, kind of like rationalizing a denominator, and you don't leave a root in the bottom. It's kind of the same idea. Okay, and next we'll look at how we simplify square roots. Okay, when you have a square root of a negative, you can simplify it. What number is in front of x, even if it's not written in this problem? Yeah, there's a -1 in front of the x. So if you want to think of it like that. It's the square root of -1 times x. Now, if you have a product, like we do under this root, you're allowed to take each factor in that product and put them into their own roots. Okay, like that. So the square root of -1 times the square root of x. And earlier we talked about the square root of -1. What is the square root of -1? I. So basically what happens is when you have a negative under a square root, the negative comes out as an I. Okay, so we don't have to go through all those steps each time. I'm just trying to show you why when we take square roots of negatives, we're going to end up just putting an I in front of the answer. And then from there, you can just treat it like it's a normal problem. All right, so let's try this one first. Okay, the square root of -7. Okay, how would I write that without the negative under the root? Yep, Sophie? Yeah, you just write I square root 7. And I didn't put a plus or minus in front of it, so you don't have to worry about that. Okay, how about the square root of -4? So this one, something's going to happen here. This one actually cleans up a little nicer than the last one did. Yep.
2i.
Yeah. So you might be thinking, well, didn't he say, the I goes in front? Why did we put the I after? Does anybody know why? I'm okay with putting the I after here, but I don't want you to put the I after it when you have a square root.
We'll be able to see if it's inside or outside of the square root.
Yeah, if you write this, it's very hard for me to tell if you mean the square root of 7i with the I under the root or not under. So we just eliminate that problem by putting the I in front. You don't really have the same situation when you have a root like that. So this one's fine, putting the I after it. How about square root of -9? 3. Yeah, that one cleans up nice. And the square root of 20,
2i squared.
yeah, you got to simplify as much as you can so the I can come out. And then 20 you can write as square root 4, square root 5. So you still need to do that kind of stuff. Square root of 4 is 2. I square root of 5. I mean, you could put I2 square root of 5, but it's just not normally how we write it. All right, any questions on that? Okay, so now we'll go through one example of add, subtract, multiply, divide, and then we can get to really the pre-calculus stuff. Okay, when you're adding, you basically combine like terms. You're allowed to add real parts to real parts, and imaginary parts to imaginary parts. Right? So what's the real part in the first set of parentheses? 7. How about in the second set?
4.
And you're adding them. What's 7 plus 4?
11.
11. Imaginary part in the first parenthesis, second parenthesis, and now you're doing -3 plus 5. 2i. Okay, that's it. So you're just combining real parts with real parts and imaginary parts with imaginary parts. Any question on addition? Okay, subtraction, just about the same thing, except think of this negative in front of the parentheses as being distributed. Okay, that's the only difference. All right, so when all right, so anybody think they got an answer for them? So,
-2 minus 3.
all right, so we got 4 minus 6, which is -2, and then -2i minus I. Some people forget that you're also subtracting the I. They subtract the 6, but not the I, so it's both. And what did you get, -3i? Perfect. Okay, so that's adding and subtracting. Similar? Any questions on that? All right, so multiplying, as long as you understand the double distributive property or FOIL, that's not too bad at all. All right, so when we multiply here, just follow the FOIL pattern. Okay, what's 2 times 5? 10. How about 2 times -I? A -2i. And how about 5 times 3i? Plus 15i. And now the last one, last part of FOIL, I'm going to look at it in a couple pieces. What's a positive times a negative? So it's a negative. 3i times I. 3i squared. And we already took care of the negative. All right. Does anybody see something I can combine here? Yep, Kate?
2i and positive 15i.
Yeah, we can combine the like terms, -2i plus 15i, and get
13i.
plus 13i. And now the last one, we have -3.
It's 3 times -1.
Right, I said don't ever leave that I squared. I squared is -1. And as Sophie just said, when you multiply -3 times -1, that turns into a +3. And now I have something else I can combine. Okay, so what would be my final answer here, Maddie?
13 plus 13.
Yep, 13 plus 13i. Just a coincidence that the real and imaginary parts came out the same. Okay, questions on multiplication? All right, so let's do a division, and then we'll pause after we do a division. Okay, so when we have a division problem, the issue is going to be we have imaginary numbers in the bottom. So we need a way to deal with that, and that's what the conjugate is going to do. Okay, so first we'll just practice finding a conjugate, and then we'll practice using it to do division. So all that a conjugate is when you change the sign of the imaginary part. Okay, that's what negate means. Make it the opposite of what it is now. Okay, don't touch the real part. Just change the sign of the imaginary part. So if I had 3 plus 2i, what would be the conjugate of 3 plus 2i? Yep.
3 minus 2i.
3 minus 2i. How about the conjugate of 4 minus 5i? Bless you. How about Kelson? What would be the conjugate of 4 minus 5i?
4 plus 5i.
4 plus 5i. Very good. Okay, how about the conjugate of 3i? Yeah.
-3i.
Negative 3i. And how about the conjugate of 6? Noah?
0.
Well, think of it this way. It's 6 plus 0i.
-6.
Just this.
Just 6. What would the conjugate of 6 plus 0i be?
-6 minus.
It'd be like 6 minus 0i. But whether you add or subtract 0, it doesn't really matter. That's the conjugate. Okay, so any questions on how to find a conjugate? Okay, now we'll use that to do a division problem. Okay, so in order to divide two complex numbers, we really don't do division. We do multiplication. And what are you going to multiply by? The conjugate. Okay? And that's going to have an effect of canceling a lot of things out. Specifically, it's going to cancel all the i's from the denominator. So you multiply the top and the bottom by the conjugate of what's in the bottom. Not the conjugate of what's in the top. I don't care what's in the top. Just the conjugate of what's in the bottom. Okay, so the first thing I want to do is look at the bottom, identify the conjugate, and then write it in the two spots I just made. Okay, so we have 2 minus 3i in the bottom, and the conjugate,
2 plus 3i.
2 plus 3i. Now we're just going to do that out, and if you do it out correctly, you will notice something very nice happen, especially in the bottom. And the top, not so much. So the top, we just do it out like a normal problem. 5 times 2 is 10. What's 5 times 3i?
59.
Plus 2 more i? 17i. And what's I times 3i?
3i squared.
Okay, we'll come back to that in a second. Now in the bottom, 2 times 2? 4. 2 times 3i? 6i. 2 times negative 3i? Negative 6i. That's always going to happen when you multiply conjugates. The outer and the inner terms always cancel each other out. They're products. Okay, and then the last part, a negative 3i times a positive 3i. Negative 9i squared. Okay, so that's a good start, but there's a lot of things we need to clean up here. So the first thing I'm just going to do is cross out the i's. How about in the numerator? What's 3i squared? Yep, it's just minus 3. And in the bottom, I have 4 minus, what's 9i squared? Negative 9. So the I squared gives me a negative, and I have that negative in front of the 9. So we'll finish it up. What's my numerator going to become? And my denominator? 13. Now, the only thing that's wrong with that is, I said when you write an imaginary number, okay, it should be your real part plus or minus imaginary part. So we don't quite have that. We have one big fraction. So what we're going to do is just take this answer and split it apart. I'm going to write my real part as 7/13, and my imaginary part as 17/13. Okay. So any questions on how I split that apart? It's just the real part over 13 plus the imaginary part over 13. And just put the I right at the end of the fraction. Okay, so that's how you add, subtract, multiply, and divide complex numbers. Any questions on that? Okay, so that's the review. So then we'll take a little break, and in a minute we'll come back and we'll start practicing how to find roots with complex numbers. All right, so now we're going to look at finding roots. Okay, the only difference from yesterday is the problems that we do today will have imaginaries, and we're not going to ignore the imaginary answers. Okay, we'll actually find them. All right, so let's start by finding the roots here. Okay, what kind of equation is that? It's quadratic. Okay, is it factorable? No. Two numbers that multiply to give you 1 and add to 1? No. So if we can't factor it, what else can we do? We got a formula. What's A, B, and C?
1.
Oh, 1. Okay, so we're going to plug that in. Negative B plus or minus, what comes next? E squared. A, C, yep, 1, 1. Over 2. Okay, so I'm going to get negative 1 plus or minus the square root of negative 3. And how do we write the square root of negative 3? I square root of 3. So that's fine if you leave your answer that way. Or just keep in mind the way on a multiple choice question you might see it written as real part separate from imaginary part. That's the real part, negative 1/2. And this is the imaginary part, root 3 over 2. And in this case, I'm okay with you putting the I after it. Even though there's a root here, I think it's pretty clear because of the fraction bar that you put the I in front. I can tell the I is not under the root. Now, if you did something like this, you would confuse me. So don't do that. Even though this is technically correct, I'm not sure if the I is under that root. Okay? So do it just like that. Okay. And that's it. Those are your roots. Any questions on that? What do you notice about the roots here? You got negative 1/2 plus root 3 over 2i, negative 1/2 minus root 3 over 2i. And they're a pair, and specifically, what's the relationship between those two? They're what? What kinds of numbers are those?
Fractions.
Fractions, but there's a special connection because it's a plus or minus. Negative 1/2 plus root 3 over 2i, negative 1/2 minus root 3 over 2i. Okay, what else in terms of what we just did? Last thing we did.
They're both divided by 2.
Yep. Conjugates, right? Conjugates are the same imaginary number with opposite, with negating the imaginary part. Okay, so 2 plus 3i, 2 minus 3i. Negative 1/2 plus root 3 over 2, negative 1/2 minus root 3 over 2i. Okay, and that always happens. Okay, so the roots are conjugates, and conjugates always occur in pairs. So when you're solving a problem and finding roots, if you find one imaginary, there's automatically another one. So the remainder theorem, the factor theorem, and synthetic division, everything we learned Monday, Tuesday, and Wednesday. Tuesday, Wednesday, we had Monday off. All those things still work. Okay, we're going to do a synthetic division one. It's going to be a little harder than the kind you would see on the test. But if you can follow what I'm doing, then the test one would be easier. Synthetic division with complex numbers is not hard. It's a lot of arithmetic. Okay, it's easy to make a mistake, so we just have to go through it carefully. All right, so I want to show that 1 minus 2i is a root, okay, or is a 0 of that polynomial. Okay, and I'm going to do it with synthetic division. Okay, so you put your root on the outside. Okay, what's the root that I'm hoping is a 0 here?
2.
What is it?
2i.
Nope, 2i is not a root. What else?
1 minus 3. Negative 1. So 1 minus 2.
So the thing you put here is what you want to show is a root. So what are they asking me to show is the root? 1 minus 2i. If they said show 3 is a root, you would put a 3 right there. The only time you switch the sign is if I ask you what is a factor. So if 3 is a root, x minus 3 is a factor. All right, so now write out your coefficients. Okay, make sure you leave enough space. And the beginning isn't too bad. Okay, bring down the 4. Okay, and this is the easiest multiplication we're going to have. What's 1 times 4? What's negative 2i times 4? And minus 8i. Now, add these columns. What's 0 plus what I just wrote? 4 minus 8i. And now, for the next 3 steps, we have to use FOIL, because we're multiplying this times that. All right, so let's go through it. What's 1 times 4? 1 times negative 8i. Okay, I'm just doing it off to the side. Negative 2i times 4. And what's negative 2i times negative 8i? 16
I squared.
I squared. All right, so we've got 4. 16i squared is really, it's really like minus 16. What's 4 minus 16? Negative 12. And what's negative 8i minus 8i? Negative 16i. And now add that column. There's no imaginary part to add, so that's going to stay. What's 17 plus negative 12? 5. Okay, and do it again. What's 1 times 5? 1 times negative 16i. Negative 2i times 5. Negative 2i times negative 16i. 32i squared.
So negative 32.
So negative 32. 5 take away 32. Negative 27. And what's negative 16 minus 10? Negative 26i. Okay, again, there's no imaginary. There never will be to add in the column. What's 14 take away 27? Negative 13. Okay, now my last step, I'm hoping that I get negative 65 somehow, because I should get a remainder of 0. If I don't, then something's wrong. All right, so last step. What's 1 times negative 13? 1 times negative 26i? Negative 2i times negative 13. Plus 26i, so that's good. Negative 2i times negative 26i. Yep, it would be a positive 52i squared,
Negative 52.
which is a negative 52.
Negative 13 is 0.
So minus 26i plus 26i is gone. What's negative 13 minus 52? Negative 65. And I have a remainder of 0. Okay, as I said, the one on the test would not be this many iterations of it. I'd take off at least 1 step. Okay, so you might have to do it twice, but not 3 times. Okay, so any questions on using synthetic division with an imaginary?
So, what is your answer?
So the question was, show that this is a root. So because I got remainder of 0, remainder of 0 was the original thing. 1 minus 2i is a root.
So is the question asking you to like show if it is a root, or is it asking you like to prove that it is already?
It's basically telling you it is a root.
Okay.
And they want you to show out the work why.
But then what would be your answer? Yes.
For your answer, I would do everything I wrote for the work and write this little statement.
Well,
Okay.
the Q, that's the R, so what will be your Q?
Oh, we're not worrying about the quotient. The quotient wouldn't even be a polynomial.
Okay.
So don't worry about the quotient, because we have all these imaginaries. And, yeah.
So we don't have to solve any of this?
No. You wouldn't be asked about a quotient. I mean, this is your quotient, but we're not going to talk about it.
Okay.
Okay.
I didn't know if it was.
Any questions on that? Okay, odd degree polynomials. Okay, I want you to picture in your head what any odd degree polynomial looks like. I'm saying that it will always have at least one real 0. In other words, it will always cross the x-axis at least one time. The same is not true for even degree polynomials. Think of a parabola. It doesn't have to cross the x-axis. How come odd degree polynomials do? Yep.
Because imaginary zeros only come in pairs. So there's an extra 0 that would have to be a real number.
Okay. Yeah, that's true. So when we're dealing with reals and imaginaries, there's different cases you could have. So like this problem is a cubic. So for a cubic, in terms of the reals and the imaginaries, you could have 3 reals and no imaginaries. Could you have 2 reals and 1 imaginary? No. No, so you can't have that one. Could you have 1 real and 2 imaginary? Yep, because they have to occur in pairs. And now this is I guess my question. Could you have this? No. First of all, because they have to occur in pairs. So I wasn't even thinking of that reason. But there's another reason I was thinking of, but that's good.
Well, it has to cross the x-axis because one, with it being odd, one goes down and one goes up always.
Right. So now you can kind of make a connection between those two reasons. Okay, the reason that you can't have that is because of the pairs, but also because when you draw this, one end goes down, one end goes up, and it's continuous. So if you go up forever and down forever, connected, are you going to go through 0 somewhere? Of course. Okay, so that's why odd polynomials always have 1 real 0. And then either one of these cases can occur. Now, this doesn't mean that your 3 real roots are distinct. Okay, repeated roots count as an answer. Okay, so maybe you see the same answer twice, or even 3 times. All right, so let's see if we can find the zeros of x cubed minus 1. Now, if you know how to factor a difference of 2 cubes, there's a formula, kind of like a difference of squares. Most people don't remember the formula for a difference of cubes. So what was the first step I did yesterday to generate a list of possibilities? Yeah, let's find all the rational roots. We'll graph it and hope that we have one. And then we'll divide through synthetically by it, and it'll turn this cubic into a quadratic that we can then solve. Okay, so what are my factors of p in this case?
Plus or minus.
In q?
Plus or minus.
So not a ton of variety here. What are all the combinations of p over q?
Plus or minus.
So if this has a rational root, it has to occur at either plus 1 or minus 1. I'll graph it really quick. Okay, and you'll see that it does occur at plus 1. And you can trace to confirm that. Okay, when you plug in 1, you get 0. So let's divide through by the root and turn the cubic into a quadratic. And the reason we're going to have to do that is because there has to be 3 solutions to this problem. There has to be. How many times does it look like it crosses the x-axis? 1 real. So what does that mean about the other 2 solutions? They could be repeated reals. We don't know that yet. Or they could be imaginaries.
Repeated always do the thing where it only touches one specific one.
When a root is repeated twice, it usually does something like, it'll come up, down, and it'll bounce away from it like that. This one's not doing that. So it's not the case where you could have 3 reals where one of them is repeated and the other one isn't. It could be the case where you have it repeated 3 times. Okay, we won't know that until we divide through synthetically by 1 and then solve it from there. Okay, so I guess technically it still could be this case where you have 3 reals all repeated, but you'll see in a second. All right, so let's divide through synthetically by 1. All right, and we've got 1x cubed, 0x squared, 0x minus 1. This one's going to be extremely fast. So we've got 1, 1, 1, 1, 1, 1, 1, 0. Okay. So in terms of our roots, we know 1 is a root. I just got a remainder of 0. Now what's the quotient? Because now I need to find the roots of that.
Quotient is x squared plus x plus 1.
Now you need to solve that. Does anybody recognize that problem? We just did that one. X squared plus x plus 1. X squared plus x plus 1. We already have the answers. Negative a half plus or minus root 3 over 2i. If we didn't have them, we'd have to do it up. Okay, but we already did. So now hopefully you can tell this is the case where you get 1 real, 2 imaginary. And the imaginary occurs in conjugate pairs. Okay, any questions on that one? All right. So what we basically did in this problem, okay, watch this. Okay, it says 0 equals x cubed minus 1. That's basically what we just solved. If I add 1 to each side, okay, watch what happens. I get 1 equals x cubed. Or x cubed equals 1, same thing. To solve this, you would take the cube root of each side. That's what we basically just did. In the last problem, we solved this equation. Right? So what we did is we found all of the cube roots of the number 1. And there's 3. 1 is a cube root. Negative a half plus root 3 over 2i, and negative a half minus root 3 over 2i. Those are the cube roots of the number 1. Okay, so we can find square roots, cube roots, fourth roots. The higher root that you find, the more answers that you get. If you want to find the 12th roots of 1, you're going to get 12 answers. Some real, some imaginary. Imaginary is always occurring in pairs. If you wanted to find the 5th roots of 1, you're going to get 5 different answers. So basically, if you set up this equation and plug in a number for the exponent, you are solving for the nth roots of what's called unity. Unity just means 1. Okay, so let's say I wanted you to find the 5th roots of 1. You would solve this equation. Right now, it's not as simple as just saying, oh, x to the 5th equals 1. Take the 5th root of each side. That'll give you one answer, but how's that going to give you all the other answers? It's not. Okay? So usually to find all the answers, it involves either factoring, synthetic division, and the rational root theorem. Okay, so I'm not going to go through and find the 5th roots of 1. We're going to do one a little simpler, the 4th roots of 1. Okay, so let's try that. So first thing I got to do is set up my equation. X to the root I want to find minus 1 equals 0. So x to the 4th minus 1 equals 0. Now you could add 1 to each side and then take the 4th root. But the problem is that's only going to give you one of the 4 answers. So what I want to do is factor this. If I couldn't factor it, I would use synthetic division right now. I would find a root. For example, I know 1 is a root, because 1 to the 4th is 1 minus 1 is 0. And I could put this down, write my coefficients, and divide through synthetically, and go from there. But if you can factor it, that's always going to be a lot faster. Okay. Does anybody see how this factors? This is really a difference of 2 squares. Yep?
X squared plus 1, x squared minus 1.
Yeah, x squared plus 1, x squared minus 1. Now, set each factor equal to 0 and solve them. Okay, so x squared plus 1 equals 0. X squared minus 1 equals 0. Okay, what do I have to do to solve x squared equals negative 1? take the square root, and remember there's always two, the positive and the negative. So what is x? Yep, those are two of the answers. And now we have to solve this one. So those are your four answers. So if someone asks you what are the fourth roots of 1, 1, negative 1, I, negative I. Okay, so it's got to be some trick that it factors, or you can use synthetic division or the rational root theorem, but there's got to be a trick to help you work it out. Otherwise, you'd be stuck. Okay, in this case, the trick was factoring.
Would it be the same if someone asked you like the x to the fourth minus 4? Would it be?
Well, those aren't, if you're solving that equation, you're not finding roots of unity. You said x to the fourth minus 4.
Yeah.
You're finding the fourth roots of 4. There are 4 answers, though. I'm not going to talk about that one right now. Actually, that one wouldn't be too bad either, because you said the number 4, so that's a difference of 2 squares again. So
What if I said 5?
we're not going to talk about that one right now. So this is actually pretty easy. X squared minus 2, x squared plus 2, and then set each factor equal to 0. And you're going to get 2 real answers, and you're going to get 2 imaginary answers. If you said 5, well, then the factoring doesn't quite work out, but there's other ways to do it if it didn't work out, but we're not going to worry about that. All right, so important pattern I want you to see in all the problems we just did, 4 through 6, the number of roots, or the number of zeros, is always equal to the degree of the polynomial. So if you're solving a 4th degree problem, 4 answers. Cubic problem, 3 answers. All right, and we're going to skip that. Okay, and the last thing I'm going to talk about is what's called the linear factorization theorem, which directly ties in with this statement I just said. Does everybody have that top statement? So the linear factorization theorem says that if you have a polynomial with a degree greater than 0, so at minimum, if you have a linear polynomial, as long as you're dealing with real coefficients, then it will be able to have at least n factors. So in other words, if you have a quadratic, highest exponent is 2. When you factor it, there are 2 sets of parentheses. If you had a cubic, highest exponent is 3. When you factor it, you get 3 sets of parentheses. Okay? So here's an example of a cubic, and this is actually what it factors into. Okay, I would expect you should be able to do that at this point. All right? The way you do it is use the rational root theorem, find a rational root. Maybe you'd find a rational root at 3, because you'd graph it and you'd see it goes right through 3 as an x-intercept. And then when you synthetically divide through by 3, this problem, you'd have 1, 0, -7, -6. When you do out the synthetic division, you're going to be left with a quadratic, and that is how it would factor, x plus 1, x plus 2. Okay? Or it doesn't really matter which root you start with. Whatever one you divide through synthetically by, the other 2 that are left would be the factors of your quotient. Okay, now that only works if you have nice rational roots. I wouldn't give you something that has roots that are really hard, like decimals. Okay. If you have something like this, keep in mind that this would come from a 5th degree polynomial. There's 5 answers here. Okay, the 5 answers are -1, -1, 2, 2, and 2. That's 5 answers. They don't have to be distinct. Okay, that's important. Answers do not have to be distinct. Yep.
Why would you say it's x plus 1, x plus 2, and x minus 3?
Yep, those are,
Why, if you do the synthetic division, positive 1 here, positive 1 here?
if you did synthetic division with a root,
I
So-
think what you wrote was like the 3, the 1, 0, -7, and -6.
yeah, I remember exactly, a 3 and then,
1, 0, -7, and -6.
yep.
But then how come you get a positive, you still get a positive 1, but yet you plug it in here?
That's different. It's x minus c, so it's supposed to, considering 3, it's supposed to be -3. So
Yeah, the number that you put as the root is what comes after the minus sign. So in this case, if I wanted to divide through synthetically, I guarantee you -1 would divide synthetically into that without a remainder, and so would -2.
Okay.
Once you can find one root that divides in synthetically, you're going to turn your cubic into a quadratic, and then that's easy to factor. Okay, so in this problem, I've just been saying to you the word repeated root. I haven't really been using a fancier term. The fancier term is to say multiplicity. So I can say that -1 is a root, or a 0, and it occurs twice. Okay, we say that it has a multiplicity of 2. 2 is a root that occurs 3 times. So we say 2 is a root of multiplicity 3. All right, so very quickly, the last thing I want to mention, we're not doing example E, but something you need to know for the test tomorrow. If I told you 2 is a root, then what is a factor? X minus 2. If I told you 5 is a root, what's a factor? X minus 5. Okay, and now you could multiply these out and get something like that. There's a polynomial that I guarantee you would have roots of 2 and 5, as long as I did it right. Same idea. If I told you 1 plus 2i is a root, what else do you know is automatically a root because they always occur in pairs? Right. That's the first thing. Second thing. If 1 plus 2i is a root, okay, pretend like that's your c, what would be a factor? X minus 1 plus 2i. Okay? And if 1 minus 2i is a root, what would be a factor?
X minus 1 minus 2i.
1 minus 2i. With that minus in there, that's a little messy. So what I normally do is write it as x minus 1 minus 2i and x minus 1 plus 2i. Now, I guarantee if you FOIL these things out, because they're so similar except for a sign, all the i's are going to disappear. And you're going to be left with a very nice polynomial, something like that. Okay, so we'll practice another one of those before the test tomorrow. Okay, so that's the homework for tonight on page 193. And remember, I'll be here early tomorrow if you need extra help.